We are going to discuss this particular topic on the principles of hydraulic machines and the hydraulic turbines. So this forms to be the part or the content of unit number 4 as far as our subject matter is concerned. What the hydraulic machines are basically to begin with. Hydraulic machines, they can be defined as those machines which converts the hydraulic energy into the mechanical energy. So hydraulic energy is basically nothing but energy which is possessed by the water, and that energy can be converted into the mechanical energy. So this mechanical energy obtained can be further converted into the electrical energy as per the requirement. Hydraulic machines are also those machines where the mechanical energy can be converted into the hydraulic energy, isn't it? So these machines are basically are the machines that convert hydraulic energy into mechanical and vice versa as well, right? The hydraulic machines, they can be either considered as a turbine or a pump based upon what type of the energy conversion they actually does. The hydraulic machines which convert the hydraulic energy into mechanical energy. So such machines are essentially called as the turbines. So that is the main focus as far as this unit number 4 is concerned. Whereas the hydraulic machines which convert the mechanical energy into the hydraulic energy, isn't it? The reverse one, from the mechanical energy into the hydraulic energy. Such hydraulic machine that we call as a pump. So we are going to discuss about the pumps in the unit number 5. So thus we can say that the study of this hydraulic machine that essentially deals with the study of the turbines, the study of the pumps as well. The turbines which we are going to focus for this unit, so that will be either a Pelton wheel or a Pelton turbine, a Francis turbine, and the Kaplan turbine. Whereas as far as the pumps are concerned, so we will focus the study of the centrifugal pumps as far as this particular subject matter is concerned. Okay. Coming on to the classification of the hydraulic turbines, the different types of the hydraulic turbines. So these turbines can be classified based upon the various criteria. One of that criteria is essentially, let us say, the depending upon the energy which is available at the inlet of the turbine. Okay, so it can be classified as the impulse turbine or the reaction turbine. Okay, impulse turbine and the reaction turbine. As far as the impulse turbine are concerned, if at the inlet of the turbine the energy is available only in the form of kinetic energy, okay, entire energy that is available at the inlet of the turbine is in the form of kinetic energy, such turbine we identify as an impulse turbine. Okay, because as the water flows over the vanes or the blades, the pressure is atmospheric from the inlet to the outlet of the turbine as far as the impulse turbine are concerned. Whereas if at the inlet of the turbine the water possesses kinetic energy as well as the pressure energy, isn't it? If the energy that is consisting of both the kinetic energy as well as the pressure energy at the inlet of the turbine, we call such types of the turbines as the reaction turbine. Okay, so as the water flows through the runner, the water is under pressure, and this pressure energy, so that changes progressively into the kinetic energy. Okay, thus in case of the reaction turbine, we can say that the runner is completely enclosed or it is placed inside an airtight casing, and additionally the runner as well as the casing, they are completely filled with the water, they are completely full of water in case of the reaction turbine. Okay, the another criteria based upon which we can classify these hydraulic turbines, so that is according to the flow of direction of the through the runner. Okay, according to the flow direction through the runner. So they can be classified as the tangential flow, axial flow turbines, radial flow turbine, and mixed flow turbines. As far as the tangential flow turbines are concerned, if the water flows along the tangent of the runner, so such turbines would be identified as a tangential flow turbine. Similarly, if the water flows in the radial direction across the runner, so such turbines are called as the radial flow turbine. And we can have the two configurations for the radial flow turbines. Okay, so they can be either inward flow radial flow turbine or the outward flow radial flow turbine. So if the water flows from the outward to the inward, that is from the outer periphery to the inner periphery of the runner, the turbine would be identified as inward radial flow turbine. Whereas on the other hand, if the water flows opposite, it means that radially from inward to the outward, it means water enters at the inner periphery and that leaves at the outer periphery. So such turbine we call as a outward radial flow turbine. Okay. Axial flow turbine, if the water flow through the runner, that is along the direction parallel to the axis of the rotation of the runner. Okay, so such turbines can be classified, can be identified as axial flow turbine. And the mixed flow turbine, so those are nothing but the combination of axial and radial. So if the water flows through the runner in the radial direction, okay, enters in the radial direction but leaves in the direction parallel to the axis of the rotation. Okay, so that is nothing but the combination of the axial and radial. They enters in the radial direction and leaves in the axial direction, that is parallel to the axis of rotation of the runner. So such turbine we call as a mixed flow turbine. Now depending upon the head which is available at the inlet of the turbine, they can be classified as the low head, medium head and the high head turbines respectively. If the head is up to 30 meters, we identify such turbines as the low head turbine. So Kaplan turbine, propeller turbine are nothing but the examples of the low head turbine. Medium head turbine, so that ranges, the head ranges between 60 meter to 250 meter. The Francis turbine are nothing but the examples which can be given for the medium head turbine. And the high head turbines, the head is in excess of 250 meters. So Pelton wheel impulse turbine is nothing but the example of the high head turbine. According to the specific speed of the turbine, so we can have the low specific speed, medium specific speed and high specific speed turbine. Okay, if the speed that is in the range of 10 to 35 for the single jet and 50 for the double jet, so those are the low specific speed. If the speed ranges between 60 to 300, medium specific speed turbine, and high specific speed turbine, that is speed ranges between 300 to 1000. We can also classify on the criteria depending upon the how the shaft of the turbine that could be placed, what is the position of the shaft. So they can be either the vertical shaft turbine or horizontal shaft turbine. So we will see in the upcoming diagrammatical arrangements the position for the vertical as well as the horizontal shaft for the turbine. And depending upon the name of the inventor who invented that particular hydraulic turbine. So Pelton turbine, Kaplan turbine and Francis turbine. Now this particular slide that shows the typical layout for the hydroelectric power plant. Okay, it is nothing but the general layout for the hydroelectric power plant. So if we look into this arrangement, so we are having a dam or a reservoir that is constructed across a river. Okay, the main purpose of the dam is nothing but to store the water, and same water can be utilized for the electricity generation purposes. Okay, then we are having these large diameter pipes, okay, which connect the dam to the inlet of the turbine. So those pipes are known as the penstock. Okay, so the pipes of the large diameter identified as a penstock. The penstock, they carry the water under pressure from the storage reservoir to the inlet of the turbine. So these pipes may be made up of the different material like that of the stainless steel, or they may be made of the reinforced concrete as well. Then we are having, say, a turbine wheel here as such. Okay, so turbine may be of the different types, either it may be impulse or the reaction turbine as such. And toward the end that we are having the tail race. Okay, so tail race is nothing but basically a channel which carries the water away from the turbine after the energy of the water has been, say, utilized in the turbine. Okay, so surface of the water in the tail race, so that is also known as the tail race. Okay, so this is nothing but a tail race at the bottom side, and on the other side, so this is nothing but a head race. And if we see the difference between the level on the head race side and tail race side, so that we identified as a gross head, that is Hg. Okay, it is nothing but the gross head represented as Hg. And here we see that there is a net head represented as capital H. Okay, so net head is nothing but the head which is available after considering the various losses. So we have seen in the earlier unit, that is the losses which are taking place when a fluid or the liquid that flows through a pipe, and we have made the calculations for finding out these major losses, which are nothing but the loss due to friction. Okay, so various friction losses are nothing but the integral part of the operation of this particular arrangement. So hence the net head available, so that will be the gross head minus the losses which are taking place due to the friction. Okay, so Hg minus Hf, so that is nothing but your net head. Okay, now if we come to the construction and the working of the Pelton wheel, so this particular arrangement, so that shows the block diagram for the Pelton wheel. Okay, this is the block diagram for the Pelton wheel. There are the four main components which are of interest to us as far as the construction and operation of this Pelton wheel is concerned. So we are having the nozzle and the flow regulating arrangement. So this is what the nozzle and the flow regulating arrangement, which consists of, let us say, a penstock, the spear as such, which is nothing but of similar to that of a needle shape. So we are having a nozzle, and we are having, say, a horizontal rod as well, so which is connected to the spear, so that may be, say, moving in the forward and the backward direction. Okay, so nozzle and the flow regulating arrangement, this one. Then the runner with the buckets, so this circular wheel that we can see, so that is nothing but the runner, and we can also see that the vanes or blades or the buckets can be mounted on the periphery of this runner. Then this dome shape arrangement that we can see here, so that is nothing but a casing, a hemispherical shape arrangement, we call them as a casing. And the fourth important element is nothing but the braking jet. So even though it has been not been shown here, but as such it would be, say, placed somewhere at the top of the casing. Okay, somewhere in the space between the casing and the vanes or the blades or these buckets. We'll see what is the function of all of these main components of the Pelton wheel. So the point to note here is that these are the four major components of the Pelton wheel: nozzle and flow regulating arrangement, a runner with the buckets, casing, and the braking jet. So as far as the nozzle and the flow regulating arrangement that is concerned, so the amount of the water which is striking the buckets or the vanes, so that is basically regulated or controlled by providing a spear in the nozzle as that was shown in the arrangement, isn't it? So this is nothing but a spear, okay, in the little shape, and the nozzle. So by appropriately moving this spear in the forward and the backward direction, so it is possible to regulate the flow of the jet of water or the discharge which is coming out of the nozzle. Okay, so that's why it is called as the flow regulating arrangement. The spear that is provided there, so that is basically nothing but a conical needle, and which is operated either maybe manually, that is by a hand wheel rotating it in the appropriate direction, and in the large scale unit, so this particular arrangement is operated automatically. Okay, so that is in an axial direction perpendicular depending upon the size of the unit as such. Okay, so when this particular spear that moves in the forward direction, isn't it, by a suitable mechanism, if the spear is, say, moving in the forward direction into the nozzle, then we can definitely say that the amount of water striking the runner, so that can be reduced. Similarly, if the spear is, say, moved in the backward direction, it is pushed backward, that is toward the left, then the amount of the water striking to the runner, that will increase. Okay, it means that the area which is available, opening which is available for this nozzle, so that can be increased or decreased depending upon whether the spear that moves in the forward direction or that moves in the backward direction. Okay, so that way the significance is there for the nozzle and the flow regulating arrangement. And coming on to the runner with the buckets, we can see here that the runner that is placed on one horizontal shaft. So this is nothing but the main shaft of this turbine, and the runner is mechanically fitted over this shaft. The runner that essentially consists of a circular disc. Okay, and on the periphery of this circular disc, the number of buckets are placed, they are fixed. Okay, and normally this number of buckets are fixed in a uniform manner, they are equally spaced, isn't it? So they are evenly spaced around the periphery of the runner. The typical shape of the bucket, so that is of a double hemispherical cup or a bowl, and each bucket that is normally divided into the two symmetrical parts. Okay, and they are, say, by a dividing wall, and that wall is normally known as a splitter. We will see in some of the next slides the arrangement there for the buckets or the vanes which are fitted around the periphery of the runner. The jet of the water that strikes, isn't it? So this jet of water that strikes the splitter, and the splitter is the one that helps to divide the jet into two equal parts. Okay, after making an impact, the jet is divided into two equal parts, and the jet comes out at the outer edge of the bucket. Okay, and the shape of this bucket is normally in such a way that the geometry is made in such a way that the jet is deflected through an angle of around somewhere in the range of 160 to 170 degrees. Okay, the buckets, they can be made of the different materials, such as it would be a cast iron, or it may be cast steel, bronze, or the stainless steel. Okay, so that may be dependent upon the head which is available at the inlet of the turbine. Then coming on to the casing. Okay, so casing is nothing but this top portion that we can see here. Okay, all this shaded portion, so that is nothing but a casing which is provided for this particular hydraulic turbine. The function of the casing is to prevent the splashing of water. Okay, and it also helps to discharge the water to the tail race. Then because the jet of water that would be striking at very high velocity, kinetic energy, and water may get splashed over a larger area if it is not provided with the casing. Okay, it also acts as a safeguard against the accidents, because the runner, that rotational speed or the RPM of this runner may be very high, 200, 500 revolutions per minute. Okay, so to act a safeguard against such accidents, the casing is beneficial for us. The casing may be made up of the cast iron, or it may be made up of the fabricated steel plates as well. Strictly speaking, the casing in the operation of the pelleter wheel, that does not perform any hydraulic function, isn't it? So it is nothing but a safety arrangement as such. Okay, in other words, we can say it is nothing but a safeguards to avoid any accidents. And on to the last part, that is nothing but a braking jet. Okay, this braking jet, so when the nozzle is completely closed by the moving the spear in forward direction. Okay, if I move this spear completely there in the forward direction, and I stop the flow of the jet of the water there in the forward direction, the amount of the water which strikes the runner, so that essentially reduces to zero, isn't it? It means that there is no jet of water that is leaving from this particular arrangement of the nozzle and spear. But even though this jet of water that has been, say, stopped, but still the runner continues to rotate, isn't it? The runner continues to rotate due to its inertia, isn't it? So due to this inertia, this runner continues to revolve, continues to rotate about its axis, maybe for a sufficient duration of the time. So it is essential for us that this runner should be stopped in the shortest possible time, isn't it? So it may be possible that the small nozzle that can be provided somewhere onto the top of the casing, okay, in such a way that it directs the jet of water on the opposite side of the vanes. Okay, so it would be, say, projecting the jet of the nozzle on the opposite side of the vanes. Okay, so it will create the resistance in the direction of rotation of the vanes or the blades. So this jet of water, so that would be identified, that would be considered as a braking jet. Okay, so these are nothing but some of the points which should be taken into consideration as far as the construction and the working principle of the pelleter wheel that is taken into consideration. I hope that this has made a sense to understand the operating principle of the pelleter wheel. This particular slide that shows the runners which can be used for the different types of the turbines. So if I see just now for the pelleter wheel, so this is nothing but runner of the pelleter wheel. So this would be, say, fitted on a shaft, and one can see that around the periphery, so such number of buckets, okay, 20-30 buckets, they are spaced evenly around the periphery of the bucket. Okay, then bucket having some different dimensions, a large size runner that can be seen in the another arrangement. These runners, runner number 3, 4 and 5, so they are utilized for another type of the turbine, that is a Francis turbine, a reaction turbine. And as far as the mixed flow turbines are concerned, so that is nothing but the Kaplan turbine. So this is the hub which is, say, mounted on the shaft, having the placement in the vertical position, and around the periphery of this hub we can see such blades are being fitted. Okay, so they may be in the numbers anywhere ranging between 4 to 6 or 7 maximum number of the buckets or blades can be mounted on the periphery in case of the Kaplan turbine. This is another pictorial representation for the Pelton wheel, Pelton turbine, and these Pelton turbines are normally suitable for the high heads. As we mentioned earlier, the high head turbines are those where the head is above the 250 meters, isn't it? So they are suitable for the high head and smaller Q. It means that the small discharges. Okay, Pelton wheel is best suitable for high head and low discharge of the water. Okay, so we can see here one of the arrangement pictorial representation for the Pelton wheel. So these are the blades. Okay, and we can see that they are having the symmetrical shape as such, isn't it? And this what we were talking about in the earlier description, that is nothing but the splitter. This is nothing but the splitter. So the jet will make an impact at the exactly at the splitter, and that will cause the jet to get deflected equally in either direction. Okay, this is the shaft of the turbine, so which is say mounted horizontally. In the another arrangement, we can see that this is the horizontal shaft of the Pelton turbine, and we are having the multiple number of runners, isn't it? So instead of a single runner, it may be possible that the multiple runners may be mounted on the single horizontal shaft. So in this arrangement, this runner number 1 and runner number 2, so 2 runners are placed on the single horizontal shaft. There is another way or the position by which the Pelton wheel can be placed. So we can have the shaft here, that is nothing but in the vertical arrangement, vertical fashion, that is shown here. This is another arrangement for the Pelton wheel, which identified as the twin jet Pelton turbine. In the earlier description, in the earlier slide, we have seen that there was a single jet of the water which is coming from the nozzle. So it may be possible that you can have such multiple number of nozzles, multiple number of the jets, right? So here we can see that this is the one of the jet. Okay, this is your penstock, and you are dividing this penstock into the 2 different sub pipes, we can say, and this is a jet nozzle for the first arrangement, this is the jet and nozzle for the second arrangement, isn't it? So this is nothing but the arrangement for the double jet or the twin jet Pelton wheel. So not only the 2 jets may be used, it may be possible that such multiple numbers of the jets can be used for the large Pelton turbines having the vertical axis. So this is what the top view that we can see, and there are the 6 jets or the 6 number of nozzles. Okay, so this is nothing but the nozzle number 1, 2, 3, 4, 5 and 6. Okay, so this is nothing but your pipe, and you are having the 6 nozzles which are placed at the different position, and you are having the Pelton wheel runner, so that is placed at the center, and the shaft is nothing but the vertical one, the axis is nothing but the vertical one. Okay, so this is nothing but the runner or the rotor wheel that will be placed on a shaft which is having the vertical axis, and the nozzles are placed around the periphery of that runner or the bucket. As far as this particular session is concerned, so we'll stop our discussion. In the today's session, we have seen regarding the classification of the hydraulic turbines. We have started with the discussion on what do you mean by the hydraulic machines. Okay, so we identified them as hydraulic turbines and the pumps. We have seen the classification for the different types of the hydraulic turbines based upon the various criteria, and we started with the discussion on one of the impulse turbine, so that is nothing but a Pelton wheel. We have discussed the schematic arrangement for the Pelton wheel, we understood the working principle of the Pelton wheel, and we have seen some different arrangements for the Pelton wheel. Okay, we'll stop here for this today's session. In the next session, we will discuss some of the important parameters which are used to carry out the analysis for the Pelton wheel, which may be used to determine the work done by the jet. Similarly, the power which is obtained from the runner, the different types of the efficiencies, mechanical efficiency, volumetric efficiency, and overall efficiency. So we'll see how these parameters can be evaluated there into the next session. Okay, so thank you very much.